Today we will talk about mesh convergence, very important aspect when it comes to do the finite element analysis. And we will see how to achieve the mesh convergence with the help of Autodesk Inventor NASTRAN. So today we'll try and find the answer for the following questions: how to decide the correct size of mesh, the process of mesh refinement, and what size of mesh is good mesh to achieve the mesh convergence. So let's start with the theory. What is mesh convergence? So uh, by definition, mesh convergence study is a process in finite element analysis to determine if simulation results are accurate and independent of mesh size. That is, if we run the two analysis with different mesh density and they give the same result, then we can say convergence is achieved. When we say result, what kind of results we are expecting? We are looking at either displacement or stress at any particular given location. So if I have the certain size of mesh, I run that analysis and I note the value of displacement and the stress. And if I change the mesh to the or I change the mesh density and I achieve the result of the displacement and stress, those are very similar, or there is no much difference between the earlier value and the new value of stress and displacement, then I can conclude that the mesh convergence has achieved, as my solution is independent of the mesh size. So that's the important aspect. And we can say when solution is independent of mesh size, we are eliminating one uncertainty from the solution and we are going more close to the correct results. Let's understand the mesh refinement process. So how to do the mesh convergence study? So we have the 3D model which is in the analysis software. We take one rough mesh size or coarse mesh size, we run the analysis. Then we again recreate denser mesh and then reanalyze and compare the result of this new finding, new results with the previous one. And we keep increasing the mesh density, reanalyze the model until the results are satisfactory, means there is no much deviation between the result of new study with respect to previous study. In general, what people say, five less than 5% difference between these values is there, then we can say the solution or the mesh is converged, or the size of the mesh is good enough to go for the final run and have the solution completed and report in the results. Uh, Now, what is why mesh convergence is important? So, if we do one particular analysis and if we don't do the mesh convergence, then whatever error that is inherited because of incorrect size of mesh will be there in the solution. So, solution is not correct if mesh convergence is not achieved. And if we use too much fine mesh, the number of elements and number of nodes will be so high that the computational time required to perform that analysis will increase, and we need to go for the higher configuration of computer or the higher hardware to run that analysis. So this is important. So having the ideal mesh size will provide us balance between the accuracy of result and output or time required to run the finite element analysis. So this is the importance related to the size of mesh and mesh convergence. So let's take one example. I have considered my very beginning study of the from the another analysis, and I start with the point 0.5 inches mesh size. So when we go into the NASTRAN environment, this is the screen capture from NASTRAN, wherein when you put on the mesh and in right click, and you will have the edit tab, wherein you can define the mesh size. So I have defined point 0.5 as mesh size, and I hit on the generate mesh. So mesh will be generated, load and everything is same. So I can see the number of nodes and number of elements, and I have noted the displacement which is in the range of 0.93, and stress is in the range of 3400 and 164 psi. So this is maximum stress, and my mesh size is zero point 0.5. In my next study, I have run the same model with same loads, and mesh size I have kept zero point 0.4. So again, I go on the mesh model, I change the mesh size, and I run the analysis in NASTRAN. So with that, I'm getting this displacement in the range of 0.928, and stress is 3500 35,861. And then again I run one more analysis with more denser mesh, and the mesh size, new mesh size is zero point 0.3 inches, and I do the same. I noted the displacement, I noted the stress value, and here is the summary of what I have done in three studies. So analysis 1 with zero point 0.5 inches, analysis 2 with zero point 0.4 inches, and analysis 3 with zero point 0.3 inches of mesh size. We can see the as my mesh size reduced, my number of nodes and number of elements have increased drastically. Then I have noted the stress, maximum stress obtained from each analysis, and I have compared the previous value with the current value, and I have noted the percentage difference between these two. So analysis 1 and analysis 2 have around 5% difference in stress, and analysis 2 and analysis 3 have 0.2% deviation or difference in the stress value. When we talk about displacement, the uh, first two analyses have the difference of 0.07%, and last two have the difference of point. So I can say by reducing the mesh size point from zero point 0.4 to zero point 0.3, my results are very much same, like my stress value as well as displacement value, that has not changed much. And this signifies my solution result are independent of mesh size. Hence I can say I have achieved the convergence on the mesh. So now we are into NASTRAN environment, and we'll see how, what are the settings and how to do that, and how it will help us in deciding the correct mesh size, at the same time having the optimal time required to run the analysis, and we will not compromise on the accuracy of the analysis. So I have run the different analysis, we can see, with zero point 0.5 mesh size, and then another one is with the zero point 0.4 mesh size, and last one is mesh refine zero point 0.3 mesh size. So here, if I right click and click on the edit, you can see that zero point 0.3 is the mesh size. Okay, and here you can see number of nodes and number of elements. We can see same data, and when we go to the mesh table, Another important aspect in the mesh, we can check the quality of mesh. So on mesh model, just right click and click on the check mesh quality. There are certain parameters and we can check with the help file from the NASTRAN what are these values. And the mesh element type is tetrahedral. We are checking three main parameters. First one is the aspect ratio, then skew angle and the Jacobian. And if we check the mesh for these parameters, so none of our mesh or the element has failed for this criteria. So the quality of mesh is good, whatever we have selected. Then there is one more thing, like mesh we can see the convergence setting. So we'll see how convergence settings or studies done. Uh, so in the NASTRAN tab, we have the convergence setting. We can do convergence setting for global or local refinement, and these are certain parameters like how many number of refinements we want to do in particular analysis. What is top criteria? It is 5%. Then element threshold from 0 to 1, we need zero point 0.9, and the refinement factor greater than 1, 1.5. We can toggle include in analysis if you want, or we can just keep as it is and we click. So when we run this analysis, while running the analysis, it will run with five different mesh sizes on its own based on the parameters we have provided in this setting, and it will check the stress value. So here is the output of the same study. So we can see on the y-axis it has taken 1 mice stresses, and on x-axis the solution steps. So we mentioned we want to have 5 steps, and it calculated this maximum stress value at end of each step, and this is same. So if it is straight line, we can say the solution or the convergence of the mesh has achieved because the value of our answer is not changing with the size of the mesh. And mesh quality check, so I have already explained this. This is the like out help file from the NASTRAN solver 2024, wherein different type of elements like quadratic, triangular, hexagonal, pentagonal, or tetrahedral is mentioned. Then aspect ratio recommendation is given and skew angle recommendation is given. So same input we have put here, and we are checking the quality of mesh. So uh, we learn that mesh convergence is nothing but having the right size of mesh, which is which will not affect the output of our of FES study, and we can solve the solution at the given time or at less time with maximum accuracy.